Okay, so if you remember last time where we were discussing product of a matrix and a vector. So there was some matrix A and then some vector X, and we get back, when I apply a matrix to this vector, we get back another vector. And I wanted you to think this in two different ways which are equivalent but they give very different physical meaning. So one way was to think that this matrix is doing nothing but it's stretching and rotating this vector to give you this new vector. The other way to think about the same thing is if you think in terms of the columns of, so let's say this is one column of this matrix, this is the other column of this matrix, like that. And if you think like this, let's say there are n columns, you can think of this multiplication like something like x1 v1 plus x2 v2.
चाचा कुछ clearly दिख नहीं रहा है.
It's not visible?
It's blurry.
Okay.
नहीं, it's blurry. It's like shaking.
लाइट की वजह से हो रहा है.
Is it because of light? Is it better? Or this way it is better. Let me try another pen.
नहीं कैमरा का प्रॉब्लम है, वो पेन का नहीं, वो कैमरा नहीं क्लियर है.
Okay. So I'll be
तो
disconnecting.
मुझे तो साफ दिख रहा है, तुम्हें नहीं दिख रहा है. मुझे तो बहुत क्लियर दिख रहा है.
नहीं, कुछ भी नहीं दिख रहा.
What can we do? Restart. Login.
क्या नहीं दिख रहा है?
Are you watching on a laptop or mobile पे कर रहे हो?
हिल रहा है.
लैपटॉप पे है.
रुको मैं फिर से ज्वाइन करती हूँ.
Okay.
क्या तुम लैपटॉप पे हो कि कैमरा मोबाइल पे हो?
लैपटॉप.
उसमें नहीं आ रहा है. ओके, तो हमको नहीं मालूम, हमको तो बहुत क्लियर दिख रहा है.
तो मतलब एक ही जगह पर, तो मेरा प्रॉब्लम मेरे एंड पे नहीं है, then it's the problem is at your end.
नहीं, तो आगे तरफ नहीं हो ही नहीं सकता.
We can restart all of us if you want. Let's restart. मैं rejoin करता हूँ.
हाँ नहीं अब दिख रहा है.
दिख रहा है?
हाँ.
Okay. So let me restart. So we started discussing product of a matrix and a vector in the last class, and this is some matrix A. It gets multiplied with this vector x to give me another vector y, and we can think of this as when matrix A applies to a vector, it rotates and stretches it to give me another vector. That is one view of seeing this operation. The another view which you can see the same operation is in terms of what it does to the vectors of the matrix A itself. So forget about this vector, start thinking about these vectors first. So a matrix is nothing but you have stacked all these column vectors together, and this multiplication is nothing but x1, if this x is composed of x1, x2 like this is a vector like this. So this multiplication is nothing but x1 times v1 plus x2 times v2 like that. And then you can say, okay, this multiplication is nothing but some combination of these vectors. So I take vector v1, multiply, stretch it by a factor x1. Similarly, I take a vector v2, stretch it by a factor x2, and keep adding all those vectors. Finally, what vector I will get is that this is this vector y. So the two things are same information but presented in two different ways. And I wanted to keep this picture in mind. So let's go back quickly to our Gauss elimination and that we were looking in the last class, and then we see cases where roots exist, root don't exist, things like that. So let's take an example and that we will use to proceed. So let's say some three variables and three equations. So let's something like, let's say x plus y plus z, and let me construct this equation right now so I know the solution. 1, 2, 3, let's say. So 1 or plus 2 is equal to 3, plus 3 is equal to 6. I'm just adding something else. 2x minus y plus z. What will this be? So 2x is equal to 2, y is equal to 2, this will be 0, so this should be equal to 3. And I'm just creating another one. Let's say 3x minus y, or let's say plus y plus z is equal to something. and that's something, let me make it 2z just for the sake of it. So it will be 3 plus 2 5 and plus 6 11. So we already know, we have constructed these equations by knowing the solution, but we fake as if we don't know. And how do we want to develop the Gauss method of solving it, which you do actually whenever you solve these kind of equations, you do that in the background, but let's make it more methodological, that how we want to do it. So let me write this. So it will be, if I write the augmented matrix of this will be 1 1 1, and then there is 6, and then there is 2 minus 1 1 3, and then there is 3 1 2 11. So this is the augmented matrix, and what we want to do in this augmented matrix, the way to proceed is that try to make it this one is already 1, so I don't need to worry about it. If this one was not 1, what I would have done is that I could have divided the whole row by some constant so that this becomes 1. So this is already 1, so I don't need to do anything. Then what can I do for the second row and third row? I can multiply the first row 2 times and subtract it from the second row. So what I can do, the first operation I can do is I can take R2 and I can do R2 minus 2R1. If I do that, what will happen, 2 times of this 1 minus 2 will become 0, so this will become 0, that is what we want to have. And similarly, I want to make this also 0, so I can do R3 minus 2R1. If I do that, this will also become 0, so let's see what it translates to. So it will translate to, the first row stays 1 1 1 6, the second row this thing becomes 0, 2 times of this minus minus 3, 2 times of this minus 1, 2 times of this is 12, 3 minus 12 is minus 9, right? And similarly 3 times of this is equal to 0, 3 times what did I do? 3R1, right? So 1 into 3 minus 3 is 0, 1 into 3, 1 minus 3 is minus 2, minus 1, and 6 into 3 is 18, 11 minus 18 is equal to minus 7. So you see, already I have made this guy and this guy 0. I am good enough. Now I can start doing the same thing. So my pivot earlier was this guy was the pivot. Now this guy is something which I want to make pivot. So what I should do, I can divide again. If I do this, R2 is equal to R2 goes from R2 divided by minus 3, so that this becomes 1. So if I do that, let me make a space here, and I'm going to do that. So the first row stays same, 1 1 1 6. The second row 0 remains as 0, this becomes as 1. Minus 1 divided by minus 3 is 1 by 3. Minus 9 divided by minus 3 is 3. So the third one stays same, 0, minus 2, minus 1, minus 7, right? Now what do I want to do? I want to repeat all over the same thing again, but now this is my pivot, right? What should I do with this pivot? I should use this pivot to make this guy 0, right? So I should try to do that, and then to do that, the recipe would be that I take R3 and I do R3 minus or R3 plus 2R1, R2. If I do R3 plus 2R2, what will happen? 2 times of this will get added to this, 2 times of this will add it to this, and like that. So 2 times of this when added to this will go from here to here, 1 1 1 6 stays like that, 0 1 1 by 3 stays like that, and now this 0 stays like this, because if I multiply by 2 and add this, it stays like this becomes 0, and this becomes 0, and then if you multiply it by 2 times, it is 2 by 3, 2 by 3 when added to minus 1, it becomes minus 1 by 3, 2 times of this when added to minus 7 becomes minus 1. You see, now I am done. So this is, if you want to think of this part, I mean the right hand side separately, this always the augmented matrix, right hand side is this. Now I am done. On the variable side, it's already all zeros below it, and now you see that if you think of this one, What is this one? This is nothing but this is saying 0 times x1 plus 0 times y2 minus 1 by 3 times z is equal to minus 1. So this last thing is nothing but minus z by 3 is equal to minus 1, or you can clearly see that z is equal to nothing but 3 here, and we knew the solution z has to be 3. So that is what we have got. So once you have this form, what you can do start doing the same thing again. So already we have this solution for z, and then I can put this value of z in second equation and I get the value of y, and I put the value of y and z from the second equation and get the value of x. So to do that, what you have to do, start doing just the reverse operation. Now do something and make this guy 0. How can I do? I can just add this and this, so it will make this guy 0. So what I do, if I do R2 goes from R2 plus R3, what will happen? The first row will stay as it is, 1, 1, 1, 6. The second row, if I add this and this is 0, 0 plus 1 is still 1, minus 1 by 3 plus 1 by 3 is 0, and minus 1 plus 3 is equal to 2. You see? And I could have, the last row stays as it is, 0, 0, minus 1 by 3 and minus 1. I could have also changed, let me do that here just for the R1 also. Let's make this guy also 0. To make this guy 0, I need to multiply it by 3. So I will do R1 plus 3 times R3. If I do that, so let me do that as well. So R1 is 1, 3 times of R3, 0 plus 1, this stays like this. This is second one also stays like that. 3 times of this is minus 1. When I add to this becomes 0. And then 3 times of this is minus 3. When I add to 6, it becomes 3. You see, I can do this step one more time. I can kill this 0 also by now doing another operation. So the final one here, where I can use this one to make this one 0. So I can do R1 goes from R1 minus R2. So I just subtract this from this. So what will happen if I do that? So the other things stay same. So let me write the other things first. 0, 1, 2, 0, 2, 0, 0, 1 by minus 1 by 3 minus 1. And if I minus this row from this row, it will be 1, 0, 0, 1. So now you see that I have made everything 0 except this one, and this is directly giving me the solution. So what it is telling me x1 is equal to 1, x is equal to 1, y is equal to 2, and minus z by 3 is minus 1, or if you want to multiply by minus 3 both sides, so it will become 1 and this will become 3. So you see, once you have made it like this, you can directly now read off the solution that x is this, y is this, and z is this. And that is what we started with. So this is the standard technique of doing the Gaussian elimination. First you start from the top to down, make it in this form. So if you see this form of matrix, how is the form? That everything below the diagonal is 0. That is what we have in this matrix. Such matrix where everything below the diagonal is 0 is called upper triangular matrix. So it's a triangular matrix, but everything only on the top is non-zero and in the below it is 0. So it is the upper triangular matrix. So you first try to get this and then repeat the same operation in the reverse way, so that now we also convert it to lower triangular matrix so that everything above the diagonal is 0. So that is what we did here. So we try to get this thing as well. Once you make the matrix both upper and lower triangle, only things on the diagonal will remain, and from there you can directly read the solutions. So all clear or any questions so far?
No, everything is good.
Okay. Now many things happen in between. So one very common thing can happen, that you can say that we started from here, we started from this matrix here, and then from there I made this 0, I made this 0, and then I said my next pivot was minus 1 by 3. Sorry, my next pivot was minus 3, which I divided by 3, I made it 1 here. So my next pivot was here. What if you get the next pivot itself 0? So suppose these numbers are such that you get this 0. If you get this 0, what does this mean? How will I proceed from here? Because in the next step I have to make this one 0, and if this is 0, no matter what I do with this, if I subtract from here, this number will not change. So you can say, okay, that doesn't matter. If this is 0, all I can do is I can swap, I can put it down. I can send this row, the whole row down, and bring this row up. So I can send this row down and I can bring this row up when this is happening. So you say, why is that allowed? It's allowed because I can write this equation first and then this equation and then this equation. So doesn't matter, doesn't change anything. So I can swap two rows if I want to. So if that happens, I can send it down. So you can keep sending down something below, not above, below, if you are getting your pivots 0. Okay, so you can't have your pivot 0 because then you will not be able to do further operations like this. But if I push it down, then it becomes 0 here, the 0 comes here, and the whatever is here comes on the top. If that is non-zero, I can proceed from there. So this tells us about a couple of things. What if you can't do it further? There are no rows below where you can swap like things like that. What does that mean, right? So let me wipe out and then explain a few cases, and then so let's take a 2 by 2 or even 3 by 3 is fine, and try to explain what can happen. This pen is not good. Okay, let me use this one. So when you have a system of equations, so the method we just saw is called Gauss method, and what you did is basically nothing. You made it first upper triangular and then lower triangular, and then that it gave you value. But in general, what all things can happen when you are solving such systems of equation. So either the set of equations that you are getting are consistent equations. Either the equations are consistent or they are inconsistent. What do I mean by inconsistent? So let's say I give you two equations. So I give you x plus y is equal to 5, and then I give you 2x plus 2y is equal to 15. The two equations together, are they consistent or inconsistent?
Inconsistent.
Why they are inconsistent, Anushka?
Because you can easily see it's happening the twice of in the second equation is basically 2 times the first
equation.
So it's not possible.
It's not possible. So what it is saying, if you think carefully, this is nothing but 2 times of this. So 2 times of this. If this is 0 here, then it is a consistent equation. That okay, both equations agree. But here, from first equation you are getting x plus y 5. And from second equation you are getting x plus y is 7.5 if I divide by 2 both sides. So they are inconsistent equation, right? So when you start doing, suppose I want to do it by the Gauss method. So what would I have written? 1, 1, 5, 2, 2, 15. And what was my algorithm? My algorithm was, this was the pivot. I used my first transformation, R2 goes from R2 to R2 minus 2 R1 to kill this and make this 0. Right? If I do that, what will happen? This will be 1, 1, 5, and the second one when I do the minus, it will be 1 minus 2 times of this, that is 0. Again 2 minus 2 times of this is 0. 15 minus 2 times of this is equal to 5. Right? You see that what does this tell me? If you see this equation, what is it telling me? It is telling me 0 times x plus 0 times y is equal to 5, or basically it is telling me 0 is equal to 5. This is not possible. This is not possible. So the set of equations that are given to you are inconsistent. So here it is very easy to see two equation case, but let's say there are hundreds of such equations and you start doing your thing. If you start doing your thing and then your pivots are 0 and you are getting somewhere, you are getting something like this, that all zeros this side and a non-zero thing this side, somewhere it starts showing up something like this, then what does it mean? That it is inconsistent. So let me repeat, what did I say? You start reducing it to get to the lower triangular form and then to the upper triangular form. If you start reducing it and somewhere if you get all zeros here and a non-zero here, then it means that the equations are inconsistent. There are no solutions and you have given me inconsistent equations. On the other hand, if this was not 15 but this was 10, was it inconsistent equation or consistent equation?
Consistent.
So in this case it was consistent, because if I just multiply by 2 both sides, so this is 2x 2y is equal to 10. So even if you, from here if you see, if you come from this row to this row to make this triangular, this will be 0, this will be 0, and so this will also be 0, because 10 minus 2 times of 5 is 0. So the third equation is telling me nothing but it's telling 0 is equal to 0, which is a valid, 0 is equal to 0. So this is fine. But then you will tell me, okay, so this is a consistent equation, but how many solutions are possible there? So you say, okay, in this case actually you only have just one equation. The second equation is nothing but the first equation multiplied by 2, and that is showing up here. It's consistent, but on this line there are no variables. All the variables have vanished, right? The 0, x1 is multiplied by 0, y is multiplied by 0, all the variables have vanished. So this line is telling me nothing new. So even though this equation is consistent, there have multiple solutions to this. So infinite number of solutions. Infinite solutions for this, because we have some rows which are coming to be like this. Okay. Then the third case, which is the case, is that actually we have two different equations. So I give you x plus y is equal to 5. So let's say that I am really creating a good equation. So 3 and 2, 3 plus 2 is 5 and 3 plus 4 is 7. So if you solve this kind of equation, then you will not get something like this. So 1, 1, 5, 1, 2, 7. And if you solve this, if I want to make this 0, I subtract, I do R2 minus R1, I'll get 0, 1 and 2. So I directly get my solution, Z is equal to 2. I can do a backward substitution to get my y, get my x, sorry, y is equal to 2 and get my x. So this is a good set of equation, and there is just one solution to this, and this solution is unique. So if you don't get any row something where 0 is equal to 0 kind of things is happening, then you will have a unique solution. Otherwise you will have multiple solutions. And if you get something like 0 is equal to 5 or 0 is equal to some other number other than 0, then it means that the set of equations given to you is inconsistent equations. Okay. Okay, so let me define a particular form of how do you know that whether there exists a particular solution or not. And there is something like you can do something where you can reduce this. So what all we are doing here in the matrix is that we are doing row operations. So if we have a certain form of matrix, what is the form? The form is that the first non-zero element in the matrix. So let's say that this one is the first non-zero element. So the first non-zero element in any row is 1. So let's make some rules. First non-zero in any row is 1. So that is true so far. Whichever is the first non-zero element, so let's say this matrix was like this. So for the second row, this is the first non-zero, right? For the first row, this one was the first non-zero. So for the second row also, the first non-zero element is 1. So far all good. Second condition I am imposing, that whenever you see a first non-zero for any row, all the other elements of that column are 0. So this is the leading one in the first row, everything in that column except that one is 0. Similarly, this is the leading element in the second row, everything in that column is 0. Here it can be anything. It can be 3 and then here it can be 4, doesn't matter. Similarly, in the third row, let's say I have 1 here and this is 0. So this one is the leading element in the third row. So the fourth element is the leading element and this is like this. Okay. So if I have a matrix like this, so let me make, okay, let me keep it some number, 3. If I have a matrix like this, let me first give you the good example, 0. If I have a matrix like this, then it is satisfying a few properties. Every first element of a row which is non-zero is 1. So this is 1, this is 1, these are all 0 and this is 1. First element is 1 or 0. Then this matrix is, if the matrix is of this form, then it has a special name. It is called row reduced echelon form. Okay, so let me make it even better actually first, then I give you a bad example. 0, 1, 1, 0. So you see that I am just putting the first leading element in every row. So this row has a first leading element 1, this row has a first leading element 1, this row has a leading element 1 and this row has a leading element 1. Whenever you have a 1 in certain row which is a leading, everything in that column is 0. Right? If a matrix is of this form, then we say that the matrix is row reduced. And if the order is also preserved, if I swap this row and this row, what will happen? This one will go here and this one will come down. If the order is also preserved, that when do you see your first one in that matrix, in any row? If in the first matrix, if you see here, if in the second matrix you get it after that, in the third matrix you get after that. If that is also true, then it is called row reduced echelon form. So even if it is something is row reduced, you can always swap it to make it to bring it to the echelon form. So if a matrix is like this, if I give you any matrix and if you start doing your row operations and you can bring the matrix to like this and you get a row reduced echelon form, then you have unique solutions. Solutions exist and the solutions are unique solutions. If you can't bring it to like this, if suppose the fourth row all becomes 0, like in our previous example, if it all becomes 0, then it means that you have less information, so less number of equations and more number of unknowns. So you will have infinite solutions in that case because you have less number of equations and more number of solutions. If you get something like this, that all zeros in the coefficients and then the y values is non-zero, then that means inconsistent values. So row reduced echelon form is basically telling you how many independent variables are there and how many dependent variables are there. So if suppose how many free variables are there basically. So suppose this was like this. So it means that there were 3 unknowns x, y, z, and we had equations for that. And if the last row is giving me this, it is basically telling me that this one is a free variable. I can choose any value I want, and once I set z, I will get my x and whatever value I choose for z, I'll get my x and y values accordingly. So this is called row reduced echelon form, that tells you in a sense that how many free variables are available. So if the equations are consistent, if they are not consistent, no questions you can't do anything further, they are inconsistent equations. But if they are consistent, how many free variables are there and how many variables which are dependent on those free variables, that if I set the values for those free variables, what will be the value of x and y. So I want you to do some exercise in your book or from anywhere. I don't want to spend a lot of time on this because this thing should be clear and move on to something else. But if this thing is not clear, We can take an example later and we can show you what we mean. But please read upon row reduced echelon form. It is nothing but what we are doing in terms of reducing the matrix to a particular form. And when you do that, if you get something like this, any line which is all zero, basically that means you have some variable which is free to, you can choose any value for that, and other variables will depend upon that. Okay? Questions? Okay, I'm slightly rushing through.
बाकी क्वेश्चंस हैं यस नो में सो गए क्या
No.
नहीं
ओके क्वेश्चन नहीं है तो बोलो हाँ ना बोलो तो बेटा
हाँ वो मैं जूम इन की हुई थी तो उसको माइक को ढूंढना पड़ा
Okay.
ओके
So what we covered is row reduced echelon form, but now let me now move little bit faster to something else, and come back to this matrix multiplication thing again. So if you think of a matrix multiplication, right? A is a matrix. It applies to a vector x and gives you something, let's say b. This is the fundamental problem of linear algebra, that we have a vector which when multiplied by a gives me another vector, and we want to find this. Suppose this is known, we want to find this. And if we want to understand this geometrically, what all we are saying is that b is given, b is some vector, let's say. If you just want to think in terms of example, this is the same example, like let's say 2x plus y is equal to 3, x minus y is equal to 5, whatever. So what is a here? A is nothing but 2, 1, 1 minus 1. So this is my a. What is my b? B is 3, 5. And what is my x? X I am looking for is the x and y are my x. And if you think of these two equations written like this, I can write it in matrix form like ax is equal to b. How I can write like this? So if you do a multiplication, for example, so if I multiply 2, 1, 1 minus 1 with x and y, so this was a and this is x, what will you get? So the rule of multiplication is take the vector from here, multiply it by this, do a dot product, so 2 times x is 2x, 1 times y is
Plus
1y, so plus 2x plus y, and similarly 1 time x is x, minus 1
Minus
time y is y, x minus y. So this is this, and I am saying a times x is nothing but this, and it has to be equal to b, which is equal to 3 and 5. Then it's the same set of equations. These two things are equal only if this is equal to the first row and this is equal to the second row, and that is not nothing but precisely the set of equations that are given to me. So if you have a set of equations, linear equations given to you like this, I can always represent it in this form. Ax is equal to b, where a is the matrix of coefficients, x is the vector of unknowns, and b is the vectors of all the right hand side values that you know. Right? So now onwards, whenever I write ax is equal to b, I will mean in general that there are set of equations like this for which you have written something like this. Okay? So if you think of vector b, so b can be something known, let's say 2, 5. So maybe 2 is here, 5 is here, so this is, let's say, vector b, 2, 5. Right? And all vector A, matrix A does that it takes some vector A and rotates and stretches it to make it vector B. So when I'm solving this problem, the question that I'm asking myself is nothing but I'm asking which is that vector x here, which when A will operate upon, it will stretch it and rotate it in such a way that it becomes vector B. So that is the question I'm asking myself, is that what is that vector x? I don't know this one, but what is that vector x, which if I operate upon by A, whenever A operates on any vector, it stretches it and rotates it. So it stretches and rotates it such that it becomes B. So that is one interpretation, or you can think in terms of the columns of x also, but whatever we think, we have to basically find for this x, and this is the fundamental problem of linear algebras. So for now, think of when we are solving this problem, we are trying to find this x. So I want you to keep this picture from now in mind, that any matrix, when it operates on a vector, it does some transformation to the vector. It takes the vector and creates another vector of it, right? So you can always think that when a matrix A operates on a vector x, it gives me a new vector, and that new vector is nothing but some kind of transformation of x. So by this T, I mean transformation. So it transforms x in some way. Okay? And we want to study a few good transformations today. And we know that what kind of transformation. This is a special transformation. And we know what it does to x. It stretches and rotates x. So we want to study that transformations today. Okay. So let's try some very simple transformations. So let's try this. I take a matrix this. So this is my A. And I take any vector, let's say I take a vector x1, x2. What does this do to this? So what will be the answer? If I multiply A and x, what do I get? 1 times x1 is x1, 0 times x2 is 0, so x1. 0 times x1 is 0, 1 times x2 is x2, x2.
Vector.
So I multiplied this vector x by a certain matrix, and I get back x only, because x was x1, x2, I get the same thing here. So this transformation is a trivial transformation. It is not changing x. Whatever it takes, it gives you back. And do we have parallel to this in our scalar algebra? So is there a number? What is the number here with which if I multiply 3, I will get back 3? 1. So this is the identity number for your scalar multiplication. Similarly, this is nothing but the identity matrix for matrix multiplication. This is identity. We call this matrix identity matrix. When it operates on a vector, it does not do anything to that vector remains same. So this is a very important one. We'll see this is we get it every time when we do some operations. So very important one. So this transformation is identity transformation, but let's make this R, some value R not equal to 1. So let's say some R greater than 0 or less than 0 is also fine. What will happen now? What is the multiplication? R times x1, R x1. 0 times x2 is 0 x2, so don't need to write anything. 0 times x1 is 0, R times x2 is R x2. Now if you think, look at this vector and this vector, then you say, wait a minute. Here I had x1 and x2. And here I have the same thing but multiplied by R. Maybe I can take this R common. I can take this R outside and I can say multiplied by R. So if I multiply A with x, I get nothing but R times x. That is, if there was a vector x, when I operate that vector x upon by this matrix A, all it does it gives me back the same vector but stretched by a factor R. So now this vector is something which is, if this length was 1 centimeter, this length is R centimeter, because everything is getting multiplied by number R. So what is this matrix doing? This matrix is doing another transformation, but this transformation is only doing one thing, and that thing is called scaling. It is just a scaling. So if I have a vector and I want to scale it by certain factor, I can multiply with a matrix like this, and whatever is my scaling factor, I can put it in the diagonal term. So see, this is still a matrix which is both upper triangular and lower triangular, because everything below the diagonal, everything above the diagonal are 0, and only on the diagonal I have numbers and the numbers are same. So if a matrix is this matrix, all it is doing, it is basically scaling a vector by certain ratio R. Is it clear?
Yeah, I get it.
Okay. So we'll see into some other transformations also, some more involved as well. But before that, what will happen? So let's say there is a transformation T, any kind of transformation, not necessarily a transformation which is coming from matrix multiplication. If a transformation has this property, let's say alpha and beta are two constant and x1 and x2 are two vectors. So alpha beta are some numbers, real numbers, and x1 x2 are vectors, right? And T might be any transformation. So you think of any transformation, like a few transformation we saw, like when matrix get multiplies to it, but not necessarily that, it can be any transformation. If it satisfies one property, and what is that property? That if this is equal to alpha T x1 plus beta T x2, if this holds, it will not hold for all kind of transformations. I'll just give you an example. But if this holds, such transformation are called linear transformation. Okay. So if this holds, so what is happening here, if you want to see clearly? There is a transformation which will get applied to this thing. This thing is some vector. How is this vector created? This is created by taking alpha units of x1 and beta units of x2. I add those things, I get some vector. Whatever is that vector, I want to transform that. If I transform that vector, and if the transformation is such that doing this is equivalent of first transforming x1 and then multiplying it by alpha, and then transforming x2 and multiplying it by beta. If these two are same, then this transformation is called a linear transformation. All good? So not all transformations will be linear. For example, if I give you a very simple example, let's say there is a transformation, and let's talk about scalars for the moment. This is some transformation which you can think of as a function for a scalar. So it takes x and makes it x square. This is a very simple function. Does this function satisfy something like this? You can see just by a very simple example that it does not, because let's say I ask you what would be T5. So you will tell me 25, because it does nothing but squares it, so T5 is 25. But you can also write T5 as T3 plus 2. Right? So you can split 5 like 3 plus 2, and it is not, if it was a linear transformation, it should be equal to T3 plus T2. But if you compute T3, it will be 9, and T2 it will be 4. 9 plus 4 is 13, which is not equal to 25. So this transformation where you demand that everything gets squared is not a linear transformation. So whenever this does not hold, it is not a linear transformation, but we are interested in cases where this is a linear transformation. So anything like this will not be a linear transformation that will happen. So what about matrix multiplication? Matrix is also doing a transformation. So if a transformation is represented by a matrix, so let's say that if I transform X, something like AX, where A is any matrix, it is a matrix, A is any matrix. If I do that, if I transform X such that it takes any matrix A and gets multiplied by this, is that a linear transformation? So what do you think? If that is a linear transformation, not, it's easy to see that, okay, what will happen if I replace it here, what will happen? So T of alpha x1 plus beta x2, you can write it as A times of alpha x1 plus beta x2, where A is a matrix. So this transformation is given by a matrix multiplication, so A times this, and it is always equal to, alpha is a constant, so it is always equal to alpha times A x1, similarly beta times A x2. right? So, and this ax1 and ax2 are nothing but you can write alpha times transformation of x1 plus beta times transformation of x2. So yes, indeed, transformation, if the transformation is given by a matrix multiplication, then it is a linear transformation, because if I have to compute the transformation of this guy, I can compute separately what will be the transformation of x1, and I can compute separately what is the transformation of x2, and then I can add it back by multiplying with alpha and beta. So indeed, matrix multiplication gives you a transformation which is a linear transformation. And the converse is also true. What is the converse? The converse is that if there is a linear transformation, there must exist a which gives you that linear transformation. So every linear transformation in the vector space is associated with a matrix, and it's true both ways, that a matrix multiplication is a linear transformation, whereas a linear transformation exists, then it means that there is a matrix which gives you that. So any question here? I know this is slightly abstract, but do you have any questions? I can give more examples. We have to actually discuss a few examples, but at this juncture, any questions?
No, can you just explain with examples though?
Okay, yeah. So we saw two examples of matrix multiplication. In one case it was identity, another case it was we just multiplied by a matrix which was still diagonal matrix, but with some value, non-zero value, some value r, so it was scaling. So let's try to see some more transformations like that to get more intuition. So what intuition we will develop maybe sometimes from the two-dimensional case, but it can always be generalized to more dimensions. So let's talk about a simple case. Let's think of this two dimension x and y, and let's think of a vector, any vector, let's say some vector this, some vector x like this. So x is nothing but, let's say, x1, x2, this vector. What I want to do is that I want to find what will happen if I rotate this vector by an angle theta. So if I rotate this vector by an angle theta, I will reach somewhere here. So this was point A, I will reach to B, and this is a new vector. This vector, new vector, this new rotated vector is, let's say, vector u, right? So I just want to find what is that matrix A when multiplied by x gives me u. So u has the same length as A. I am not changing the length. I am not stretching this vector x. I am just rotating it by an angle theta, right? So what would be that matrix A? And can we figure out what that matrix A would be? So it's an anti-clockwise rotation of theta, and you can derive it easily using some geometry, that what it should be. So what we want is that what are the entries here when I multiply it by x1, x2 gives me y1, y2. This is x1, x2 are known. These numbers are known. I want to know this number. To know this number, I need to know what should be here. That matrix, whatever is that matrix, we'll just see what that matrix is. That matrix is called rotation matrix. Okay? And since this transformation is given by a matrix multiplication, this is a linear transformation. And what would that be? That rotation matrix would be? Any guesses? Or do you know it already? If not, let's try to do it by geometry. So what is this point? This point was x1, x2, because this was my original vector x. This point was x1, x2. what we want to know is what these points are, y1, y2. So I want to write y1 and y2 in terms of x1 and x2 and this angle theta. So if I use geometry and then if you see y1, how much y1 is? So y1 is this length, right? So I can always say y1 is equal to this original x, this minus this. Can I say that? Similarly for y2, I can always say it is equal to this plus this. So you can always use your geometry to write what y1, y2 would be. Let me write the answer first so that I don't remember what exactly it should be, but I think I do. Let me write it first. Okay, I think this is it and we can test. You can always write it from geometry and then you can see that this is the factorization you get back. But let me write it first and convince you that this is this. What will happen? What should this matrix be? So let's say this is the rotation matrix that rotates something by angle theta. Let's call it t theta. What should this be if theta is 0? If theta is 0, it means that it should be a matrix which is doing nothing. If you give you x, it should give you back the same thing, because if I am rotating by 0 angle, then as if I am not rotating. So does that satisfy this? If I put theta is equal to 0, this will become 1, 1, 0, 0. So this will become 1, 0, 0, 1, which is the identity matrix. If I multiply the identity matrix with x1, x1, x2, I'll get back my x1, x2, and that is good. That is what I wanted. So similarly, you can work out this whole thing, that this thing should be the rotation matrix for this transformation from the geometry. I'm not going into deriving this, but if you have a problem, you can derive this easily. You just have to write what is y1 in terms of x1 and x2, similarly y2 in terms of x1 and x2, and this angle theta, and you can factorize this. So maybe that is an assignment. So let's try this. Let's work upon this. So I will keep this separate, and I ask you this. There is a vector 2, 3, and my theta is pi by 3. How will this rotation matrix, if I rotate this vector by an angle theta which is equal to pi by 3, what is my new vector? So that is the question. What will I get? So I have 2, 3 somewhere here. I rotate it by pi by 3. So what should I get? What is my new vector? So this is 2, 3.
Minus.
It's gonna be
Yeah.
Minus
So what should we do first? We should find out what is my transformation matrix. So what is my transformation matrix?
cos pi by 3.
Cos pi by 3, which is
wait.
1 over square root of 2.
no
1 by 2.
No, 1 over 2. Sorry.
1 over 2.
Sin
Sin pi by 3,
Negative square root 3 over 2. 3 square root 3 over 2.
and this is back 1
And
by
1
2.
over.
So now if I multiply 2, 3 with this, I'll get my new vector, which is 1 by 2 into 2, that is 1, minus root 3 by 2 by into 3, so minus 3 root 3 by 2. Right? And that gives me a suggestion that it looks like it is wrong. It should be,
Shouldn't it be minus
yeah,
2,
it should
3?
be like this. My transformation matrix is like this. Minus will come here. So 1 by 2, oops, when can we come? 1 by 2 times 2 is equal to 1 plus root 3 times 3 root 3 times 2. That is the first one. And similarly it will be minus root 3 plus 3 by 2. Have I done it right? Can you check it is all good? So I put theta is equal to pi by 3, I get my transformation matrix. I multiply the original vector by that, and whatever is the multiplication, that is my answer. And I think this was right, Anushka. No, it was not wrong. This was okay. This was right. So once I know the transformation matrix, it's very easy for me to come up with any matrix which is to come up with any vector which is nothing but a rotated form of some vector. So okay, let's try something more easy, which is easy to see. What will happen? What is this vector? 1 0.
1i 0 y.
So 1 0 is a vector. Where is that
1i
vector?
0 0
That vector is 1 unit from here, right? So this one. What if I rotate it by pi by 2? What will happen? What is the new vector? So you say, okay, with pi by 2, let me write my matrix. So cos pi by 2 is 0. Sin pi by 2 is 1. Sin pi by 2 is 1. Cos this thing is 0. So this is my transformation matrix. And if I multiply 1 0 with it, what will I get? 0 times 1 is 0, minus 1 times 0 is 0, so this will be 0. 1 times 1 is 1, 0 times so 1 0. So what will happen if I rotate it by pi by 2? I get new vector which is 0 1, and that is what I see in the picture as well. If I had this vector, I rotate it by 90 degree, I get this thing back. Okay, you can try different angles and you can try rotating with that. Okay, so this rotation matrix is a very important matrix, and it comes very often when you are doing any problems related to geometry or mechanics or many other things, any coordinate transformation where you are doing that. Okay, what if, so let me further take it further from here. So this time I wanted to do something different. This time I wanted to do, I had a matrix X, I had a vector X, and I want to rotate it by an angle theta, but I also want to scale it. So after doing that, let's say I am doing this. I want to get this Y, right? So the scaling is by a factor, let's say by a factor R. So if this length was, whatever was this length, this is R times that length. Of course, in this picture, R looks like less than 1, but that is what I want to do. So you say that, okay, wait a second, I already know what I need to do for rotation. So for rotation, I have to multiply this by a matrix T theta, which is this matrix. So if I multiply T theta into X, I will just rotate this matrix by an angle theta. So it will be something like this. But you don't want me to get this, you want to squeeze it. So I also know how to scale. I have already learned how to scale a vector. And how did we scale? We scale by something like this, R0, 0, R. So a matrix which scales by a factor R is given by this. So not just, I should not only rotate it, I should further scale it also by a matrix SR, where SR is nothing but a matrix which scales.
R0, 0, R.
Right? So I will have, first I will do a rotation and then I will do a scaling. If I do that,
Can that happen the other way
in
around?
this case it can happen other way around as well, not in general. So I can do that. So what is happening here? So this is one matrix and this is another matrix. I am multiplying two matrices. So there is a matrix A and there is a matrix B, and I am multiplying two matrices, and then there is X. So you can read it in two different ways. You can read it as if the matrix B operates on X and gives me something Y, and then A operates on that Y. Okay, so that you can think of it in that way. You also want to think it, you can also think in different ways. You can think of A is some transformation, B is some transformation. When I do AB, this is a compound transformation or composite transformation. I am composing a new transformation which does both A and B. That new transformation applies on X. So you can think of it both ways. So you can try to do an assignment where you take a vector x, rotate it by some angle, whatever angle, let's say pi by 4, and scale it by 2 times. See what the matrix that you get. What matrix you will get? The matrix that you will get is basically R0, 0R, cos theta minus sin theta, sin theta, cos theta. If I do a matrix multiplication like this, what will I get? It is a 2 cross 2 matrix. This is also a 2 cross 2 matrix. This is equal to this, so multiplication is feasible. Once I do this multiplication,
2 cross 2 matrix.
the remaining thing is 2 and 2, so that I'll get back a 2 cross 2 matrix. And what will be that 2 cross 2 matrix?
R cos
So take this
2 by 2 again.
2 by 2 and let's find out what that matrix will be. So this vector
R
multiplied by this vector,
R cos theta
r cos theta, plus this 0 multiplied by sin
Zeros,
theta
which
stays
is
0.
nothing.
Then this vector multiplied by this vector
minus R sin theta.
minus r sin theta, and then this 0 multiplied by this cos
Doesn't
theta
matter.
gives you nothing. Then this 0r multiplied by this, 0 into cos theta 0, r times sin
R
theta
sin
is
theta.
r sin theta,
And R cos theta.
and similarly r cos theta. So this matrix, which is doing both rotation and stretching, is nothing new, but whatever was your rotation matrix, if you multiply by
scaling.
every term by r, then this matrix is doing both stretching as well as rotating. The stretching is happening by a factor r, the rotation is happening by an angle theta. Okay, so this is our rotation matrix. So it's a linear transformation. Why it is a linear transformation? Because it is given by a matrix multiplication, and matrix multiplication is nothing but a linear transformation of the vector. Okay. We can spend more time on rotation, but let's cover a few more transformations which are useful. And when you are solving problems, I mean, you will find very interesting problems which can be based upon this, and we can revisit if you want some of those problems later. Okay. Let's say this is a line, L, right? And let's say this is a vector x. Again, we are taking inspiration from 2D, which is easy to draw, but the same thing can be generalized, same formula can be generalized to any dimension, because we are not restricted to 2 dimensions. 2 or 3 dimensions we can plot and we can see, so that's why we use that. Okay. What we want to understand is something called the projection of x on L. So L was some given vector and x is also some given vector. What we want to define is projection of x on L is basically, if you want to think of it geometrically, you can think that this x is composed of 2 things. One thing is something which is aligned along with L in the direction of L, and the other one is perpendicular to this. So I can say it is x parallel and x perpendicular. So this symbol is denoting perpendicular and this symbol is denoting parallel. Right? So basically I am saying x can be written as one vector which is parallel to the line, given line, and another vector which is perpendicular to the given line. I can always represent it like this. The component, this one, is called the projection of x along L. So if I project this thing along L, whatever I get is this thing is the projection of this. So how much will be this thing? That is what we want to know, right? And how, any idea how we can get this? So let's say from geometry, if you want to try, right? So
Like what angle should be rotated by in order to obtain that vector?
yes. So let's say this angle was theta, right? And if you just think of them as 2-dimensional vector, I can always think of a vector dot product is nothing but, if I take the vector dot product x dot L, right? So it is nothing but it's equal to the length of vector x times length of vector L times the angle cos theta between them, right? What I am interested in is basically this thing, which is nothing but whatever is the length of x cos theta. If this is x, this angle is theta, this thing is x cos theta, right? So we are interested in knowing this. And if I take a dot product, I get the term x and I get the term cos theta, but I get something extra L. So to know x cos theta, this is what the projection was. I can always divide it from this side.
Couldn't we say the tan of this angle should be x parallel by x perpendicular?
Yes, but we are interested in knowing this given this,
Oh,
right? So even this is unknown, right? So we were interested in this x cos theta, which is nothing but if I take the dot product between x and L and divide by the length of the L, then whatever I get is the projection. So now I get a rule that how can I get projection? The rule is that whatever is the vector, take the dot vector product of that vector with the given line and divide it by the length of that line, you will get your projection. So let's try to do a projection for some vector, and this is the picture I have drawn is for 2D, but the concept the same concept can be stretched to any dimension. So let's say we extend it to some other dimension. Let's say x is 2, 3, 4, 5, and let's say the line L is any line 1, 2, 0, 1. I want to know the projection of x along L, and the rule is take the dot product, doing this dot product and take this dot product and divide it by the length of L. So what is the dot product between this vector and this vector? If it is represented in this form, then I don't do this kind of thing. I can just take the dot product of this and this. So 2 times dot product is this times this is 2. Sorry. 2 into 1 is equal to 2 plus 3 into 2 is equal to 6, 4 into 0 is equal to 0, and 5 into 1 is equal to 5. So this is x dot L. And how much is that?
Aki, you want to say something?
No, I was just
8
saying
and 5?
Yes.
13. So x dot L, the dot product is nothing but 13. What is the length of L? The length of L is square of this plus a square of this plus a square of this, root of that we learned in the last class. So 1 plus 4 plus 0 plus 1, which is root 6. So how much is the projection of x along L? Is nothing but the length of this projection. The length of this projection is nothing but 13 divided by root 6. That is the length of this projection. Okay, so now you understand what do we mean by projection. Projection is like there was some line x, I want to see how much its component is along this line, and that is the projection of that we get. Okay, so far so good? Any
Yeah.
question? Okay,
No, I'm good.
not good?
No, I'm good.
Okay. Okay,
You also explain the span, subsets, and all those stuff.
we will, it will come.
Okay.
Right now I'm just trying to get you to a few transformations which are important.
Okay.
Okay. Okay. So now we know the length of this thing, right? We know the length of this thing is this much, but I want to write this in terms of vectors. So I want to write it like a vector which is in this direction L, which has a length this, right? How can I write that? So I can say, okay, I know the vector L. If I divide it by the length of vector L, I know the unit vector in this direction. So if you consider this, This is a vector whose norm is 1, right? Because if I take the norm of it, it will be norm of this divided by this. This will cancel. So this is a unit vector along this direction. So how can I write this vector, which was the projection? I know its length was x cos theta, right? And then I multiply it by whatever this vector L is, and I get back my the vector which is in this direction and which has a length of this. Okay, all of this I can write in terms of matrix, and if I am able to write all of this in terms of matrix, then that matrix will represent my projection matrix, and we are interested in that projection matrix P. Okay, how should I go from here? Let me write it like this. Let me take an example and we proceed from there. So let's say my vector x was x1, x2. My vector L was L1, L2. Okay? And I want to write what is the projection vector along this. And how can I write it? So first thing I have to do, I have to compute x dot L, which will give me a number, and then this is divided by the length of L, which will give me the size of vector which is in this direction and which has this size, and then I have to take this thing and I have to multiply this number by L1, L2, because this is the L that I want. So I need to compute this. 1 second, let me. Why L is coming twice? Let me first write what the projection matrix will be. I want to derive it for you, but I am just trying to see that it's easy. L1 square plus L1 L2, L2 L1 L2 square. Okay. So let me write it directly, and then I'll convince you that this is the projection matrix, which will come from here. To do the derivation, it will take a lot of time. So let me just write it directly what this is. So if my x is x1, x2 and my L is L1, L2, then I am saying that this is a projection matrix. The projection matrix is such that if I do P times x, then I will get a vector which I was interested in, and that vector was in this direction and equal to the projection of x along this direction. So its length will be this. This one should be divided by 1 by root of L1 square plus L2 square, that is length of this. So this is a multiplication factor, and this is the projection matrix. So this projection, if you take this projection matrix and if you multiply any vector, then it will give you the projection of that vector along that L. So let me take an example and we can prove it with that. So let's say x is some vector 3, 4 and L is some vector 1, minus 1. Okay, so I want to get the projection of x along L. So what I will do, I will first create my projection matrix P, and my projection matrix P is nothing but L1 square. L1 square is 1 square, that is 1. L1 L2, that is minus 1. L2 L1, that is minus 1. L2 square, that is 1. So this will be my projection matrix multiplied by the length of, divided by the length of this, so 1 over root 2. So this is my projection matrix. So if I want to take the projection of x along L, what I will do, I will compute this P times x. So P times x is nothing but 1 minus 1 minus 1, 1, 1 by root 2 is there, and this x was 3, 4. So if I do that, 1 times 3 and minus 1 times 4, which is equal to minus 1, and minus 1 times 3 is equal to minus 3 and plus 4, which is plus 1, and divided by root 2. So this would be the projection vector of x along this line L, right? So you can always create projection vectors like this. So take an example, if I take a simpler example where you can see what the projection should be. Let's say 4, 5. This is my x, 4, 5. And let's say line L is this x-axis. So this x-axis is my line L. Okay. I want to take an example where you know the value 3, 4. Okay, so this vector is basically vector 3, 4, that its length is 5 from the Pythagoras triangle. This is 3 and this is 4, right? So if you take the projection of this vector along L, you should get 3. So let's see whether we get 3 from this or not. Okay, so what is my L? L is a unit vector along, let's say, x-axis. So it is 1, 0. So from this L, if I create my P, this P will be equal to 1, 0, 0, 0. Right? L1 square is 1, L1, L2 is 0, L2, L1 is 0. This thing is this. Okay? So now if you do P times of this 3, 4, so let me do P times of 3, 4, so that is 1, 0, 0, 0 of 3, 4. What you get? 1 times 3 is 3 and everything else is 0, so you get 3, 0. So you see, I had a vector 3, 4, I wanted to project it along this axis. When I do that, I should get something along, so this is nothing but 3 times of 1, 0, which is the right number, because this is what the projection is, it's a 3 unit vector along line L. So projection, if you want to find the projection of any vector along any other vector, first thing that you need to create is a projection matrix. From that vector, from that line L, you can create it like this. If this is not in 2 dimension, if this is in multiple directions, you can extend the same formula. But once you have the projection matrix, you can multiply the vector with that to get your projected vector along that line, right? So if let's say this was not in 2 dimension, it was in n dimension. So your L is something like this. So it's in L1, L2, like that up to Ln. So if someone says what is the projection matrix for this line L, so I'll write my P is equal to L1 square, then the second one will be L2 square, like that, Ln square, and this one will be L1, L2, L1, L3, like that, L1, Ln. Similarly, this will be L2, L1, L2, L3, like that, and you can fill the whole matrix with the same pattern. You see that this is a symmetric matrix. This is equal to this equal to this, like that. Everything above the triangle, above the diagonal is same as everything below the diagonal. So this projection matrix is a symmetric matrix. Once I know the projection matrix, I can project any vector that you gave me by multiplying with the projection matrix. Okay? So, any question about projection matrix?
No, it was clear.
It's clear. Okay.
Yeah.
So now, if I ask you this one, that what is the value of this guy? So now I know what is my parallel vector. To get my parallel vector, I will do P times of x, right? So this will give me this projection vector. What is this one? So what is this vector? So this vector, you can always write that my x was nothing but x parallel plus x perpendicular. So this x was nothing but this vector plus this vector. I already know this guy now. So to know this one, so I can always write x perpendicular is nothing but x, the original vector, minus the parallel vector, right? And this I already know. This I already know. I have a way of getting it. The way is that I know the projection matrix, so I multiply the x with the projection matrix to get my. So the perpendicular one, if I want to know, I can know very easily by subtracting it from the original vector. I get back my perpendicular one, and this takes us to the next transformation, which is called reflection. So what's reflection? So let me draw this picture again. It has become cluttered, so I'm just drawing it again. So this is some line L. Think of this as a mirror, that this is a mirror, and this is some vector x. Okay, so L is a mirror. What will be the mirror image of x in this mirror? So the mirror will, if this is the perpendicular, the image of this x will be this x dash, right? So image of this x in this mirror will be this x dash. What if I am interested in knowing what this x dash is? How can I know that? So it's easy, because now if you think of what is x dash, so x dash is what this vector plus this vector, right? And what was x? X was this vector plus this vector. Now I know both component of it. I know this component, which was the projection of x, and this component, which was perpendicular, x perpendicular, which we already know now that x perpendicular is nothing but x minus projection of x, right? So to get this one, if I see the projection part is common, but now I have to add this one to this, but by taking a minus of that, because the original x perpendicular was this direction, and in the mirror it will be in this direction. So this is nothing but minus of x perpendicular. So I can always write x dash is equal to x parallel minus the projection minus the perpendicular part. And if I write that, so x parallel is nothing but p times x minus x perpendicular was this guy. So if I do a minus, I will get a x, and then minus and minus will become plus, so I will get a p of x. So if I do this, 2 times p of x minus x. So p was a projection matrix. So if I want to get my x, I have to do this, and if I take x common, it will be 2 times p minus identity times x. So x dash is nothing but 2 times of the projection matrix minus identity. If I take I common, if thing were a scalar, if I take something common, I get 1. In vector, if you take a vector common, you get an identity matrix as a common. So I get the I from here, and if I take x from here, the 2p is there. So this is the matrix, 2p minus I is the matrix, which will tell you that with that matrix, if I multiply my x, I will know where the reflection is, what is the reflection vector. So this thing is called reflection. So any question about this? Is it clear, or you want me to take an example to do some exercise so that it becomes clear?
Can you repeat it? Sorry, I did not get it.
Okay. So from where? Since the beginning or since?
No, from this time, from the after the PX.
Okay, let me say it from the beginning so that even if you miss something.
After the explaining the parallel part.
This one?
Perpendicular. Yeah, after that.
Okay. So my intention is that this was my vector x pointing to some point A, and its mirror image is here, let's say A dash. So the original vector was x, and the mirror image is vector x dash. I want to get this. How is this x dash created? This x dash is nothing but this vector plus this vector, and this vector is nothing but negative of this vector, because the perpendicular part for the original vector was in this direction, and I want the new vector in this direction. It's the same distance but perpendicular of it. So then the mirror, this distance is equal to this distance, but it is in the opposite direction, so this is minus of x perpendicular. So if I write px minus of x perpendicular, px minus of x perpendicular, I should get my x dash. So px and x perpendicular, we already worked out that it was x minus px. If I put it again, it will be minus x plus px. So px here will become 2px, minus x is minus x. And if I want to take x common between this and this, so if I take x common, it will be 2p. If I take x common here, instead of 1, you will get an identity matrix, because if you take a vector common, you get an identity matrix there. So 2p minus I will be your matrix. With that matrix, if I multiply x, I'll get my x dash. That is the mirror image of this. If you want to take an example, let me take a quick example. Let's say that L is some direction 1 by root 2, 1 by root 2. Okay, so L is some direction like this. Why I have taken 1 by root 2, 1 by root 2? Because it makes the length 1. So L is a mirror. This vector is denoting a mirror. And now you are interested in any vector. Let's say the vector is 3, 4. Right? So you are interested in vector 3, 4. And you want to know that if this is my vector x, if I take the mirror image of this vector in this mirror L, what will be the new vector? What will be the vector which will denote the mirror image? And let's try write that by x dash. So that will be nothing, but to do that you need to compute 2p minus I times x. And so before working that, we need to know what is p. So p we already saw. P was of the form L1 square, L1 L2, L1 into L2 square in 2D case, divided by the length of L, which is already 1, so I don't need to worry about that. So this one will be equal to half, 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 half. Right? L1 square is half, L1 L2, everything is half. So this is my P. And what is my I? My I is identity matrix 1, 1, 0, 0. So what will be 2p minus I? 2p minus I will be nothing. If I multiply everything by 2, it will be 1, 1, 1, 1. And if I subtract 1, 1 from here, it will become 0, 1, 0, 1, 0. Do we see that? You see that this, if you do 2p, it will be 1, 1, 1, 1. If you multiply a matrix by a number, everything gets multiplied by that number. So 2 times p is, everything is 1. And if I subtract I from there, so I has got 1 here and here, so those terms will become 0. And the terms and the numbers here and here will not change, because I has got 0 in those terms. So I'll get this matrix. So once I get this matrix, to know the reflection x dash is nothing but 0, 1, 1, 0 times 3, 4. And if you do that, you will get 4, 3. So the reflection of point 34 in this mirror is nothing but 0.43. So it will just switch. The x-axis and y-axis are just going to swap each other. So 4 will, this is the y, this will become the x, and this is the x, this becomes y in this particular mirror. Because what is this mirror? If you think carefully, if I draw carefully this mirror is nothing but a line at a 45 degree. So L was nothing but a line at 45 degree, and 3, 4 was a point here. 3, 4 was a point here. In this mirror, if this was the mirror, if you take the image of this point, it should be somewhere here. On this line, x and y are same, because my L line, L was like created like the same way, x and y was same, so this was 45 degree. If you take an image of this it will be at 0.43. So that is what you get in the end. So this was the original vector x, and this is the vector x dash. Are we good? Is it clear now?
Yeah, it's good.
Okay.
Thank you.
So we learnt about a few transformations. Let me do one more actually. That comes rarely, but yeah, let me do one more. So we learnt about a few one, right? We learnt about how you can rotate, how you can scale, how you can rotate and scale together, how you can take the projection, and how you can take the reflection, right? There are many exercises in your book, so I don't know whether you, I just was glancing through your book, so those exercises are very good, but I'm not sure what all the syllabus entails, but those are very good exercises if you want to do to get practice. There is one more which is called sharing. Let's say x1, x2 is my x, some vector, and I'm looking for a matrix which does something like this. It keeps one of them same, and let's say do this, k times x2 plus x1. So the new mate y is this, and I'm looking for a x equal to y, so I'm looking for a which does this. The a which does this is called shearing transformation, and it's the word shearing basically means that one surface is slipping on top of another surface. So physically this kind of transformation occurs there. So what can this a be? So if you want to take a guess, what should this a be, so that kx2 plus x1, but it can be other way around as well, x2 plus kx1 as well. So what can this be? Any idea?
One.
Actually let me do this, it is better. x2 plus kx1. If I do that, x2 plus kx1. If I do that, yeah, so you're saying something 1. So
Yeah, 0,
0,
k, and 1 again.
k and 1 again. Will it give me that?
Yeah.
Let me see. So 1 times x1 plus 0 times x2. So this thing is satisfied. Then k times x1 plus 1 times x2. This is satisfied. So this is my shearing transformation. Okay. So whenever this apply, why this is shearing is that you can see some examples, like let's say this is some deck of cards are I keep it here. So this is a deck of cards. So these are like 52 cards. I'm looking it from this direction, so the cards are like this, right? I'm just drawing the side diagram, so I will not draw this. So the cards are kept like this, right? And now suppose you start slowly moving this thing to some angle theta, right? So what will happen when you rotate to some angle theta, this will still be straight, but this card has not moved. The card on the left, this one has not moved. Nothing has happened to its base. Its base is still here. But the card which was here is now here. You see that? In between, this card will move somewhere here. This card will move somewhere here. So I'll have a slope like this. So all the cards have slipped on each other like this, right? So if you think of the coordinates of this point, so originally whatever it was, now one of the coordinate has stayed the same, the x coordinate has stayed the same, but the y coordinate has increased by some amount, and that some amount is proportional to the x coordinate. So that some amount is proportional to the x coordinate. So the y coordinate has increased like this, and that proportionality is this k. So that's why this matrix is related with shearing, because whenever one surface slips on another, we call it shearing impact. So here all the cards are slipping on top of one another. and this matrix represents that thing. Okay. So how much time? What's the time now? I think we should stop here and let's do. If you have any questions, I can address that, but we should not progress further from here today. So, any questions that you have from previous class or today's class, we can discuss.
No, I think I'm good.
Okay, good. So,
Oh, I had a problem assignment to do, and I was given an equation where I had. Okay, I can explain you the equations. So
yeah.
एक minute.
तुम अपने से करो पहले बेटा, उसके बाद
No, I
चाचा
did it by myself. I just want to confirm it if I did it right or not. So like it was एक minute मैं ढूंढ रही हूँ.